Today the topic of the lecture will be on recombination mechanisms. We have already seen that recombination can be broadly divided into radiative and non-radiative. So at the beginning I'll talk about different radiative recombination mechanisms. These, as we will see, are the reverse of the mechanisms observed during optical absorption. The first mechanism that comes to mind is that of exciton-based phenomena, which are observed in very high purity materials. We've already seen that an exciton is nothing but a bound electron hole pair which has a certain binding energy. The pair is electrically neutral, and it takes a certain amount of energy to dissociate the pair into free electrons and holes. So excitonic mechanisms are seen in very pure crystals, which are grown by MBE or metal organic vapor phase epitaxy, and at very low temperatures, because at higher temperatures the exciton breaks up into free electrons and holes. So a simple way of looking at this is by looking at the band structure again. This is EC, the band gap is EG, and since free electrons and holes reside in the bands, whereas the exciton has a binding energy, say E exciton, so when recombination occurs from a free exciton to the valence band, the energy involved, H cross omega, is equal to just Eg minus the energy of the exciton. This is for a direct gap semiconductor. For an indirect gap semiconductor, this mechanism is much less probable, and the energy is H cross omega is equal to Eg minus E exciton minus or plus the phonon energy involved. What does the spectrum look like when in, say, gallium arsenide? At very low temperatures, typically at 1.6 degrees K. This is VPE grown, very high purity. The intensity, if we plot the intensity versus wavelength in angstroms, we'll be able to identify many of the recombination mechanisms. Starting off with a lower wavelength, higher energy, going to, say, longer wavelengths, the spectrum looks something like this. we can identify many of the features starting from a feature at the lowest wavelength, highest energy, which is recombination due to free excitons. This is called Fe. Now, in addition to free excitons, excitons can be bound to either donors or acceptors. And these donors and acceptors can either be neutral or charged. Typically, in this case, in the case of gallium arsenide, we find that this peak intensity is due to excitons bound to neutral donors and having a ground state n is equal to 1. The feature here, exciton bound to a positively charged donor. This peak is due to exciton bound to an neutral acceptor, n is equal to 1. Remember, excitons have hydrogen-like states with different values of n equal to 1, 2, etc. Here there is a feature, this is D0x, n is equal to 2. And finally here we have D0x, n is equal to 3. The wavelengths are typically here 8200 angstroms. So in this spectrum of very high purity gallium arsenide, we find that there are D0x, this is neutral donor, bound exciton. We have A0x, which is a neutral acceptor, bound exciton, and we have D plus X, which is a ionized donor, bound exciton. The question arises, how do we identify these levels? We identify the levels by both looking at the energies which can be calculated, the energies of these specific levels, and also their line widths. It turns out that the line width of bound excitons is equal to about 1/10 of the line width of free excitons. So this gives us a clue. And secondly, the emission energies of bound excitons is somewhat lower than the energies of free excitons, as we saw on the previous graph. So the energies and the line widths enable us to identify what are the donors and acceptors and the excitons involved. Obviously, we can get a clue from analyzing the material as to what are the donors, what are the acceptors present also. The concentration of donors and acceptors can also be estimated either through resistivity Hall effect or through directly through SIMS type of experiments. So in very high purity,
Sir, why high purity required?
Because if you have lower purity material, then the excitons break up with interaction with the carriers. The excitons are not stable, they break up very easily. So in that case, we have band-to-band recombination. Free electrons combining with free holes. This is observed at higher temperatures than for the excitonic mechanisms, and one can say that for this the energy kBt must be greater than the energy binding the exciton. If the energy is slightly higher, then obviously excitons dissociate, and also at higher carrier concentrations. When the local fields, remember higher carrier concentrations mean that there are local fields due to donors and acceptors break up the excitons. Obviously, in this case, we are looking at direct recombination between electrons and holes. So the low energy cutoff will be Eg, but one can get emission at, suppose one could get the low energy cutoff will be Eg, but one can get recombination at slightly this is intensity, and this is lambda going that way. Okay, so energy is increasing this way. And we know this is obtained at moderate doping concentrations. At higher doping concentrations, we have all the earlier effects that we discussed, band tailing, Moss-Bernstein shifts, and finally we have band gap shrinkage. This tends to come in at doping concentrations of the order of 10 to the power 17 and higher. The excitonic mechanism is present for low doping concentrations, 10 to the power 13, 10 to the power 14, low 10 to the power 15. Band to band is 10 to the power 16, 17, and then at higher doping, all these effects come in. Again, just as in the case of absorption, we have for direct gap semiconductors, we have an expression that the light intensity as a function of frequency is given by h nu minus Eg to the power half, whereas for indirect, light intensity is equal to B dashed H nu minus Eg plus EP squared, where EP is the phonon emission energy, and therefore we find that we plot L against H nu. We find for direct gap, light emission increases in that fashion, and for indirect gap, whereas the cutoff here is Eg, and for indirect gap it is Eg minus Ep. The expressions for B are known. This is given in terms of the effective mass twice Q squared mR, the reduced effective mass, which we've seen before, to the power 3 by 2 over n, over constants n, and R C H squared ME star, where MR is the reduced effective mass. 1 by MR star is equal to 1 by ME star plus 1 by MH star. These band-to-band transitions are what are required in optoelectronic sources like lasers and LEDs operating near room temperature with appreciable doping. There are other types of transitions that are due to deeper levels. For example, just as in the case of absorption, if you have a semiconductor with donor levels, then one can get transition of electrons from the donor to the valence band, or from the conduction band into acceptor levels. The probabilities obviously depend upon, in this case, it depends upon the number of electrons in the donor level, which is say ND, and in this case it depends upon the number of electron has to go from the conduction band to the acceptor, so the acceptor must be full of holes, and this must depend upon Pa, the concentration of holes in the acceptor. Now, whether these transitions dominate or the band-to-band transitions dominate depend upon the recombination rate, which is again determined by the lifetime. Calculations have been done for direct gap remember, the transitions are deep, almost near the band gap. For example, this energy will be just Eg minus Ea, right? And here it will be Eg minus Ed. But the levels themselves are shallow. These are shallow donors and shallow acceptors. Okay. Typically, this energy will be something like 7 MeV for gallium arsenide, and this will be something of the order of about 28 MeV for gallium arsenide. So having known what these values are, if you know the band gap, you can know where to look for these particular transitions. The question is, which transitions dominate? Do band-to-band transitions dominate, or these transitions dominate? So that can be estimated by looking at the lifetime for these two different processes. Suppose we have shallow impurities. Discrete. That means the concentration is not so much as the wave functions overlap, non-overlapping. The wave functions of the electrons bound to the donors or acceptors do not overlap. With these approximations, it has been possible to actually calculate what are the lifetimes for the donor to valence band transition at k equal to 0. It is found that 1 by tau p0 is equal to, there's a large number of, there's a big term comprising just constants, 64 root 2 pi n c cubed m squared mc e d to the power, this is the donor energy, to the power 3 by 2 q squared h squared omega is the frequency. This is the matrix element PVC squared for transition from the conduction to the valence band into ND. This is the concentration of electrons in the donor, because this determines the probability of these electrons making a transition from the donor to the conduction band. Here, the material terms are N, the refractive index, omega is the frequency, ED is the donor ionization energy, and PVC is the average interband matrix element of the momentum operator. For the conduction band to acceptor transition, a similar expression has been found. The lifetime of electrons is given by the same the same constant as here. The only difference is that we have here we have MA EA to the power 3 by 2 corresponding to the acceptor ionization energy, and we have PA, the concentration of holes in the acceptor level. So here EA and ED are the donor and acceptor ionization energies, and ND is the concentration of electrons in the donor. PA is the concentration of ND is the electron concentration in donor, and PA is the whole concentration in the acceptor. So if all these are known, one can actually estimate tau P0 and tau N0 and compare it with the band-to-band recombination probability, and it's found that all this is very simplified. The results have been calculated. For gallium arsenide, 1 by tau P0 is 0.8 into 10 to the power minus 8 into ND centimeter cubed per second. This is 1 by tau P0 is obviously the rate of, and 1 by tau N0 is 0.43 into 10 to the power minus 9 PA centimeters cubed per second. Suppose we put in values, say, we assume, say, ND and PA are of the order of 10 to the power 18 per centimeter cube. We can calculate these values, tau P0 and tau N0. There's a difference of a factor of about 5. These are of the order of, say, 1 to 2.5 into 10 to the power nanoseconds. Okay. If ND and PA are smaller, then obviously, these 1 by tau P, the rates are even smaller, and lifetimes will therefore be larger, right? How does this compare with band-to-band recombination, transition probability? Band-to-band recombination transition probability, again for gallium arsenide, is given by 1 by tau n 16 n q squared w by c cubed m squared h over the same matrix element. And if you put in values here, tau n comes to about 0.31 nanosecond. So you see that this is, so this tau n for band to band is of the order of say 1/5 to about 1/10 that of tau P0 or tau N0. So obviously, for these doping levels, band-to-band recombination is much more probable, is faster by a factor of 5 to 10 over recombination through impurities, donors and acceptors. And so this is a much faster, this is a faster, and this is a more probable process. Okay. These are important because, as you know, in all active materials, we have a certain amount of donors and acceptors, and they play a major role. However, there are sometimes undesirable or deep levels in semiconductors, and they can also give rise to recombination, which are sometimes undesired. For example, in gallium arsenide, one has iron gives a deep level at 0.36 eV. Nickel gives a level at 0.35 eV. Copper gives a level at 0.345 eV. So this is the band gap of 1.45 at 77K. These levels are 0.35 eV above the valence band, and as a result, if you look at the spectrum, the emission spectrum, you find that there will be if this is the band-to-band recombination at 1.45, there will be recombination due to iron, nickel, and cobalt round about 1.1 eV. If you look at these, obviously, iron, this could be nickel, and this could be cobalt. So one gets a band of energies quite separate from the band-to-band recombination at much lower energies due to these deeper levels. And as you know, some of these deep levels are, say, chromium in gallium arsenide is near the middle of the gap, and it is used to make gallium arsenide semi-insulating. But it is not desirable for the point of view of making light-emitting sources, lasers or diodes. Now we come to another very important mechanism, that is direct donor-acceptor recombination mechanism. I've already talked about the donor-acceptor absorption. So this is the counterpart. We have a material with both donors and acceptors. Then if the acceptor contains holes and the donors contain electrons, then obviously recombination is possible. An electron moving from a donor to an acceptor, and what is this energy? In this case, h nu is equal to Eg minus Ea minus Ed. But because the donor is positively charged and the acceptor is negatively charged, there is a binding energy plus Q squared epsilon of the semiconductor, epsilon 0, epsilon r into R dA, where R dA is the donor-acceptor distance. Between discrete donors and acceptors in the semiconductor lattice. This value of R could be something between 10 to 40 angstroms, which will give you discrete lines in the spectrum. But if this is more than, say, 50 angstroms, then the number of lines merge and then you get a broad band. And at about 200 angstroms, because the distance between donors and acceptors becomes large, the probability becomes small, and then you get a cutoff. What is the nature of the spectrum? This donor-acceptor pair, DA pair recombination mechanism, has been studied in detail in materials like gallium phosphide, in cadmium sulfide. And for example, it's found that one can really identify, say, if in the case of gallium phosphide, one can identify, this is the intensity of luminescence versus energy. This is broadband for large distances, and then one can identify individual peaks for discrete donor-acceptor distances, for specific distances between the donor and acceptor. Now, if we look into this in a little more detail, we can see that, say in gallium phosphide, we can have two types of donor-acceptor pair recombination. For example, in type 1, we can have the donors and acceptors both sitting on the phosphorus site. What is a typical? We can have silicon sitting on phosphorus site, group 4. This is an acceptor. And we can have, say, sulfur sitting on phosphorus site. This is a donor. Right? And if you think of the gallium phosphide lattice, zinc blend, say these are phosphorus atoms, so one can have a silicon sitting here on a phosphorus site, which is acting as an acceptor, okay, and a sulfur sitting here, which is acting as a donor. So the distances are obviously going to be, the smallest distance is going to be this, and there are a number of such donor-acceptor pairs. The next nearest neighbor will probably be this. Okay, all the donors and acceptors are sitting on one sublattice. Okay, so one can actually calculate what are the donor-acceptor distances, discrete allowed distances. This is the first one, this is the second one, etc. Okay. Now, the second type 2 donor-acceptor pairs, are when in gallium phosphide, say we have zinc sitting on gallium site, giving you an acceptor, and we have, say, as before, sulfur sitting on phosphorus site, giving you a donor. So in this case, obviously, the distances are going to be different. Zinc sitting on, this is, say, gallium site. So zinc sitting on gallium site gives you an acceptor. And sulfur, this is the sulfur can sit here on the phosphorus site, okay, gives you a donor. So the donor acceptor distances here will be different from that in the type 1 case. And the interesting feature is that specifically these lines have been identified, and one has a series of donor-acceptor recombination lines going up to about 50, which have been identified in gallium phosphide. Suppose you take the type 1 case in which you have silicon and sulfur as the impurities. It has been found that one gets, in addition to specific lines, one can get phonon replicas if we have 0 phonons emitted, we get the emission here. Suppose during this donor-acceptor pair recombination, 1 phonon is emitted, we get this line, 2, 3, 4, 5, 6, etc. And since the phonon energies are known, 0.048 plus minus 0.002 eV. We can identify this, and then we notice that these phonon replicas occur at regular intervals, separated by this phonon energy. So this is a case in which donor-acceptor pairs are accompanied by these LO phonons. So these are again interesting features that can be identified. Now, the last topic I'll discuss is PL in quantum wells, which are important for devices. This is a case of band-to-band recombination, except that in the quantum wells, the electrons are localized. So this is the quantum well typically made out of gallium arsenide, whereas the barrier is made out of aluminum gallium arsenide. And we know that this is a case of an electron in a potential well. These energies are given by the well-known Schrödinger formulation. And for the case of electrons in the conduction band, we have that these energies EL are given by pi squared h cross squared L squared over twice ME, where ME is the effective mass over LZ squared, where L can take integral values 1, 2, 3, etc. So we can put E1 is the lowest one, this is 2, this is 3, and LZ is the width of the well. So LZ plays a major role, as we'll see, in determining the spacing between these levels. Similarly, for holes in the valence band, the lowest level is EHH1, because the hole effective mass for heavy holes is larger, so the energy here is smallest, and we have a series of levels EHH1, HH2, etc., etc. So what is the energy of emission in a quantum well? The lowest energy is H cross omega, which is equal to obviously EG, EG say well, plus E1 plus EHH1. We'll see that the quantization criteria in which we, for the effect of the quantum wells to be felt and observed in luminescence, we should have the difference in energies between the levels EL plus 1 minus EL should be greater than kBT. The thermal energy for gallium arsenide with Me star is equal to 0.063 M0. We have the interesting condition that levels are really quantized at 300 K for devices. This is the one that is condition that is important. If LZ is less than 150 angstroms. And if LZ is greater than 150 angstroms, then the luminescence pattern, that in this case the energy difference will be less than kBT, okay, and then you have bulk-like recombination. The effect of the quantum wells are not felt. So, in this talk we have discussed various types of recombination mechanisms. We started with excitonic mechanisms, then band-to-band, deep level, donor-acceptor pair, and finally we've discussed photoluminescence, that is recombination in quantum wells.